Hello everyone, my name is Ashley Alfred and the subject matter for this project is improving the identification of foodborne pathogens in chickens using hyperspectral data. This first diagram shows you the process of getting hyperspectral microscopic data or HMI data and then using the information you get from that data, which is spatial and spectral information, to identify the pathogen. What we want to do is improve the HMI data before using it in identifying or classifying pathogens. So the method that we are exploring is using compressed sensing or CS for feature enhancement. I learned about compressed sensing in the context of addressing the limitations in MRI data collection, where the general idea was to determine the smallest number of random samples that produce a good enough brain scan reconstruction for doctors to analyze, so that they wouldn't have to take so many samples from their patients. Typically, CS cares about the smallest percentage, in that when creating the starting image that's used to test the reconstruction method or the algorithm, the sampling scheme uses a small percentage of the original scan. And so since we are looking at CS for feature enhancement, we actually want to use most of the data. And so we sample at 90%. And our starting image would reflect that, and you'll see that later on when we talk about data visuals. So if we look at the method, we are minimizing the L1 norm subject to the following constraint. And the problem statement is cast into a second order cone problem, and we can write the objective function, and it's solved using the interior point method via the log area function. And we also must compute the gradient and the Hessian, and after that we can solve the system of equations. Now the data for this poster, if you look at the first diagram, you see an image that has a number of cells in it. That's how the data comes to us. So we pick a cell and we extract the hypercube for a single cell so that we can have a single cell hypercube. And the image underneath data represents three slices or wavelengths. One from the front, one from the middle, and one from the end. And so this is for the bacteria of E. coli or Escherichia coli. And then this plot underneath that in data represents the spectral signature of this single cell. So if we move on to the data visuals, we have SSIM and PSNR plots. These are popular image metrics used to quantify image similarity. And so the SSIM is showing that the L1 minimization performs very well, and you can quantitatively, you can see that because the closer the SSIM value is to 1, the better. And then I have some specific image slices that you can see representing specific frequencies or wavelengths. And you can also visually see it if you look closely at the image. You can see that from the starting to the recovered, it has improved very well. And again, the difference would be much clearer if we were not sampling so high, but we are sampling at 90% because that's what we want to do. And so the PSNR plot shows the same thing. The higher, the better, and all the values are higher. We also looked at the changes between the original and recovered images using a heat map, and we can see here a bright red spot here in the edge of the bacteria, and that indicates a strong sharpness in the edge. We also looked at the feature importance values of the two images, and we see that most of the features had an increase in importance, except for one being negatively impacted. So we have some conclusions, which are, everything that we said going over the data visuals. We have successfully amplified a rough feature, and our future work is to use more single cell data, more E. coli single cells in different bacteria as well, and show the effect on the classification accuracy. I would like to thank my advisor, Dr. Sue from the math department, and Dr. Park from the USDA.